Okay, should be great. Go ahead.
Okay. Hello, my name is Nina, and today I'll be talking about the paper, the Language Models on Biomedical Data Analysis, a survey. But specifically, I'm going to talk about one specific mechanism in LLM. So, okay, let's first read the abstract.
Well, I think it's the first time to handle the review in the journal club because it's usually challenging. Okay. Do you think everyone for the abstract?
Clear.
Very clear.
Yeah, this is a very straightforward abstract. So the red part is the gap sentence. Just emphasizes that we need to know more about LLM. And that's what I'm trying to explain for today's presentation.
Yes. Before everyone think about this abstract, I know it's very straightforward, clear, but it has one key feature why it makes too easy to understand. Can you count how many times LLM and biomedical, these two words are repeated? 3, 4, more than 5? Yeah, it's a lot, right? So I think he or she did it on purpose. So repeat the two keywords a lot of times. So when you finish reading this abstract, only 2 words are left in my brain. LLM and biomedical. Okay. Does it make sense? Yes, this is also good strategy.
So, like the papers or the abstract said, we need to know a little more about LLM. So, I'll start talking about it. So, a few years ago, computers couldn't understand a simple sentence. So let's say I said, I bought cookies at the store, it was delicious. So in our head, we will think of a delicious cookie like that. And this is because we know it is referring to cookies. And we know that delicious is associated with food. This means that humans understand the context of a sentence. In the past, however, computers couldn't understand what it was, so it would sometimes think that it is a delicious store. And this is because computers couldn't understand the context. And now LLM was able to fix this. To develop LLM, transformer was an evolutionary finding. So as you can see, in 2017, there was a paper called Attention is All You Need, which was viral for their title, and it was cited by a lot of people. And because of this paper, we were able to interact with ChatGPT. So we know how important LLM is and the transformer model is. So now we're going to talk about the transformer model. So let's say we have this sentence, the curious cat chased big butterflies in garden. So in the transformer model, the question is asked, how is cat described? And we can answer, cat is curious, like that. And then another question we can ask is, what is cat doing? Chasing, like that. And then there can be way more questions for the model to learn about this sentence, like this. So how can transformer define all these connections in between words? And these are defined individually with a mechanism called attention. And attention can answer individual connection questions that will create the whole transformer model. So this presentation will focus on the attention mechanism. So to only focus on the first question like that, so in attention, it sets a goal. So the goal is the question, where it's how is cat described? And then we're gonna shorten the input, so we put the curious cat chased. And then this is the attention formula that I will go step by step, but for now, the input needs to go into this attention function. So the first question we can ask is, how do we plug a sentence, a word, into a math formula? So our first step of attention is embedding. What embedding does is it turns sentences into vectors / numbers. So what we can do is we will list out all the inputs, so the, curious, cat, chased, and then it'll train from a big text model that you can find easily. So this work as like a dictionary. So what does the mean? What does curious mean? And it'll spit out values like this. So it says, so for these values, we can kind of define what it means as well. So on the top it says living things. So this whole column represents whether the word is living or not. So
It's a probability between 0 and 1.
yes. Yes. And the high value represent living, and low values will represent non-living. And then another embedding can be related to action. So we can say that chased is can lead to high values because it has action, but cat isn't. And we can kind of define each of the words with different embeddings like that. So this whole matrix is called the embedding matrix, which is the meaning of the words. So now with this embedding matrix, we can apply this attention function. But first, we need to convert these embedding matrix into these attention inputs, which are Q, K, and V. Like that. So first, let's look at what Q is. So conceptually, Q is asking what is our main focus. So again, our goal is how is cat described? And our main focus is where is cat? And query can, for us to convert the embedding matrix to query is through this formula. So we can easily multiply the embedding matrix to the tunable parameter. So these look like random numbers because it starts as a random number at first, but through iterations, it'll tune the parameters. So it kind of works as like a hyperparameter in like machine learning models. So these are basically the weights to answer the Q. So if we multiply these two matrices, we will get a query matrix. And this query matrix basically means how important each words are. So what this means is that, again, our query goal is where is cat? So if we focus on this cat values, we see that it has high values, high weights, because we want to know that we want to know what is important or not, and these are not scaled from 0 to 1. It can be over that, but this is just an example.
So, yeah, I have a question. So, embedding matrix is very clear.
Yes.
Query is also very clear. But the two-number parameter, this two-number parameter matrix is keep changing depending on the question.
Yes.
So, but how do we know that what kind of question we will do?
So it's first, so based on the model, it first starts randomly. So they're
Okay,
all
randomly.
random numbers,
Okay, and then?
but after going through like loss functions, it'll tune the parameters
So
to.
here, what would be the loss function? What do we want to reduce? Here, do you know? That part is confusing
Yes.
to me. Is there anyone about element in this room? Translation? Do you know? Okay.
Yeah, so it's like a kernel in a
Uh-huh.
in a neural network. These are the trainable parameters. The W is one of the kernels.
So
What is it? What is the loss function? Well, I think that's really zoomed out from this.
Yes.
Uh-huh.
Like these types of attention mechanisms end up in a lot of different kinds of neural networks. And I think here in the large language model, you're predicting the next word in a sentence or something. So I don't know that. I don't know. So
I think
hopefully
here
it turns out.
one missing part is what we want to optimize by doing this. Kind of, for instance, can we predict the next word better? Something like that? Or whatever, yeah.
The examples I saw that I've read about are translation.
Translation become better.
Yeah, so then the loss is easier to understand for translation, like how close to the translated sentence that you get. That's not what you're gonna talk about, right?
Yes, but the paper itself uses the example for translating from English to I think German or something. So, but it is like from like it's the tuning the parameters is not happening here. So it's in like a
I'm sorry, I studied the LLM since yesterday. I haven't reached this part. I cannot help you. Anyone?
Well, also, I mean, you look at the past, before they started doing this, you had like recurrent neural networks and LSTMs. The idea was to so time in this case is the word in a sentence, right? So like pseudo time. So processing the meaning of curious in the context of the sentence would come from the previous words in the sentence. And they didn't work real well because you always give a lot more weight to the words that are directly before. Right? But sometimes as you nicely showed in your example at the beginning, the context can really span the entire length of the sentence.
Yes.
So this is processing everything in time simultaneously.
Okay, gotcha.
Okay, of course, it'd be lovely to do that, but we don't have computers that,
I see.
right, that can maybe do that. So another important part of this is they make the computation to process the entire sentence tractable. It's efficient enough.
Okay. So
that's a huge part of this attention thing.
Okay. And everyone just keep this WQ in your mind and then let's move on, but we will get back. Let's try to understand the context of LLM.
Yes.
Okay. But by the way, this attention score was developed by your alumni, Professor Jung Yeon-jo at NYU. He's your math department graduate, Kais. He's the one who developed that score, attention score. Yeah. Cool, yes. Go ahead.
Okay, so again, the cat values will have a high score in the query because that's what we're looking for. Okay, so we know what a query is, and then now we're gonna focus on what K is. So now that we know where cat is, K is asking what connection are we looking for? So now we have the position, but now what kind of connection in between words are we looking for? So K is key, and then in this context, we want to ask which words describe, or specifically which words describe cat. So it's obviously curious, but we can go through the same process like the query, where it has a different tunable parameter, the weight, to answer key. And then if we repeat this, we'll get the key matrix. And if we look at the values, the values mean how describable each words are. So if you look at the values the, it has a very low value. It's because the can't describe anything. But if we look at curious, it has a high values because it is able to describe something. So if we go back to our attention equation, it says we need to do a dot product in between Q and K, T, and I'll show you what the dot products will represent. So we have our query that shows how important each words are, and then we have the key and how describable each words are, and then we have to transpose to match the dimensions. And then we will find the dot product like this. So this is just a dot product of the query the and key the, and then query the and key curious. So this basically means, this number means that can curious describe the? If it does, it has a high value. And how important is it? And then if both of these questions are true, it'll give you a really high value. So we would kind of repeat the same for all these queries and values. So all these values basically mean the importance of two words connection.
I see. That means basically Q is indeed about the cat.
Yes.
Actually, I think we missed the goal. Goal is how is cat described? To answer this question, they dissect this question to the cat part and describe part.
Yes.
And then Q is about the cat, K is about the describing.
Or how it's connected.
Yeah, and then their inner product should be both are satisfied.
Yes.
So everyone, is it clear?
So to kind of
This is what you learn at the high school, isn't it? Inner product is common component of the two vector. And he got 16 million citation. Good, okay.
So to focus a little more on the values, so again, if we focus on 0.29, it has a low importance of curious describing the, because it's kind of impossible for curious to describe the. But if we look at the highest value here, it has a high value because it's important that curious is describing the in our goal.
Cat describes cat. Why would that have a high value?
So
It seems a little reductive.
Cat.
So when I was like watching the videos, it says like usually it has a high value when like a cat is describing cat or like the same like the correlation between the same words. So I think that's why. But not all cases have the question or the goal how is cat described. So
Well, look at the diagonal entries.
Always.
The doesn't describe the.
right.
Curious barely describes curious.
What about in this way? Cat and curious has sort of a high correlation.
Mm-hmm.
So that cat curious cat, sort of the indirect correlation. Like a describe no, but cat describe cat. Maybe there is some indirect overlap. That's why cat could be high. You can see that maybe curious might be also could be higher than other thing because curious, cat and curious. That could be
maybe still the connection is not so because the cat value is high because it is important.
Yes.
It's more so that importance score affected that value. I think that's why it's much higher than the other diagonal.
I think the diagonal is sort of describing something else, not how cat describes cat. It's more, I think what you guys are saying is just how important cat is.
Yes. Okay, so with these values, again, it just shows how important word connections are. And then, so after doing the dot product, we can kind of expand our formula into dividing it, doing the softmax. So it's just the process of normalizing. So with our matrix that we got here, we wanna divide by the square root of dimension of k. So this, I believe, from the explanation that I read, it was similar to like cosine similarity where you have to normalize. And in real life, this matrix here actually will contain a lot of bigger values and a lot of smaller values. So that's why we kind of want to scale it. And I think that's why the author chose that to scale this matrix.
What does softmax do?
So what softmax does is, so after scaling, these will be the values that we'll get. And it will, so all these values will equal to 1. So all these will be in the range of 0 to 1. And if you add them up, it'll be 1.
So why does root decay matter then?
Because if we don't do this, then and if we go through softmax, okay, so let's say we have like and if these values are very big, sometimes softmax only will focus on one value. I mean, if we, sorry. Yes. So with no normalizing, softmax will only focus on one value and give it a high score. But to
I think because the softmax function includes exponential function, so that's the reason why we like describe like that. Because
It doesn't cancel out when you take exponential, these are log.
also
Yeah, 정리
I think
나갔어요.
we can write E. So the softmax function
Yeah, good teamwork. They sing together.
like this, so it should be it isn't scale.
It doesn't cancel out that way.
Yeah. So we need
Thank you.
we need to scale.
Q.
전후에 좋다.
So yeah, the weighted, all these values will be, or all these numbers are weighted equally through the range of 0 to 1.
The vertical is also one? Some?
No.
Only row
Only,
is.
yes.
Okay.
So now with this, our last step is to multiply v in the equation. So what is v? So v is what information does each words carry? So I kind of assume like the whole softmax function as a weight of, like as a new weight of the each words. And then now we multiply that with what actual information does each word carry. So it's really similar to Q and K, where you have to multiply by the tunable parameters that'll answer the value. And this part is a little hard to explain, like what is a high value or what is a low value, because it can carry a lot of like information that we couldn't understand through numbers. So I will just leave it at that for values. Oh, and then I kind of want to explain, I was at first confused between the value and embedding matrix because they both mean meaning of words. But the value here will contain more information about the context due to their tunable parameters. Makes sense.
Wow. Heating of weight. So softmax it was square matrix, right? Okay, square matrix times that. Oh, yeah.
So lastly, we can combine all the matrices together. So we have our softmax weight and then our value. And then if we multiply the two, we will get our new embedding matrix that contains information that is newly informed. So now it's with context. So again, these words or these numbers are a little hard to interpret because we're not really sure like what big numbers mean and what low numbers mean. But what the new embedding matrix will do is basically shows you that now cat row, these numbers are now including the curious context. Okay, lastly, so what we just did was turn out our goal and put it into a tension function, and then we got an answer like curious. So this whole sequence is called a single head attention. So if there's single head, there should be multiple. So now let's go back to our previous questions. So what is cat doing? Chase. So now we can set a different goal to get a different answer. And then we would want to repeat this until we fully understand the the sentence. And the paper concatenates all these matrices to create this image or to understand the sentence.
So that means, what is cat doing then? Only K will be changed, and Q will be the same. From Q will be changed or not? K will be changed.
All three.
All three are changed here? Because
I think that the weight matrices
Ah,
are
yes.
assigned for each attention function, and they hold them, the parameters would be trained to minimize the loss function of the last image, maybe.
I see.
So actually, so we are explaining it this way. So each attention plays this role, this role, this role. But I think that is automatically trained, and we explain it in that way afterwards.
So the computers actually don't ask this because they wouldn't understand it. These are just computers are all just numbers and parameters, but this is an interpretable way for us to understand this.
But the embedding matrix is constant in the whole process, right?
Yes. So it goes through one same trained model.
The other way to understand this is it's just a class of nonlinear functions, parameterized by those weight matrices, and all of this attempt to understand the meaning is nonsense.
Wow.
Yes.
So, basically saying we give many attention structure to the model, and each attention structure trains each context,
Yes.
and then final outputs are used as a predictor.
Yes. Yes.
But this is efficient because each head can be processed independently. It can be
Yes. And at the
multiple
same
machines, right? So remember, you gotta get the whole time sequence, but you have to do it efficiently, and that's really what is achieved by
That's why
multi-head
they need a
attention.
lot of GPU.
That's right.
So ChatGPT actually uses 96 single head attentions. So, and obviously it goes through a lot of more advanced like other functions, but just looking at the attention itself, it uses 96 attentions.
And the dimension of the embedding space,
The embedding, like which embedding space they use?
well, you have the initial embedding of the sentence, right? That's important. You had 3 in your,
The number
Yes,
number
so
of
it's
columns.
not 3,
Oh.
it's like a million or I don't know.
Yeah, there's a lot that I can't remember off the top of my head because it was a really big number. Yes, but it has a lot of big embedding matrix. So actually in the paper, it kind of visualized how like each attention can be shown. So let's say we have this sentence, well, we don't really have to understand this sentence, but for one single head attention, like you can think of this as a query and a key and like how each are connected. So like this is what one attention does, it like kind of shows a connection in between words and how strongly connected they are. And you can see like a slight difference in the second attention. Other connections are stronger in the second attention, and like it goes on until it fully how many attention heads you have. Actually, that is it. I think these are the take-home messages. The embedding, QKV, and adding, concatenating all these together.
Okay. Yeah, I know, we had a lot of questions during the chat, but any question?
So I did not really completely understand what is a single head attention. Like, can you explain again and also say whether it's filled by the user, like somebody asked this single, write this single head attention, or is it just generated by the computer?
Oh, so these questions are for our understanding. It's usually just all numbers, all parameters. So I put this as an example because that's how humans understand, but computers don't actually ask, like, do I want to understand this part or not? And yes, so the whole process that I said, so like the first, so the goal, how is cat describing curious and answering curious, that is one single head attention. And this is the second single head attention. And then it goes on. Does that make sense? So like that one process is single head.
Okay. And the way I see LLM are like a little bit like neural networks in the sense that you have massive parameters and
Yeah.
this wave matrix what you train basically. But I didn't really understand, like, you did not really explain how we train this data, so I'm curious, like, what kind of data do we need to train this model?
So it's basically how I interpret it was first how it's embedded. So how is the model gonna understand a single word? So for example, if we have like the word Harry, we can have Harry Potter or Prince Harry. So it'll have all that knowledge in their head. And so I think that's why in like biomedical sense, we can choose a model that is related to what we want to train. Does that make sense? I don't know if that makes sense.
No, I think you're right. So remember, what you really want is something that operates on language, written language, with the success that neural networks have been applied to images. And one of the things that made the image stuff so powerful is that you could have this very difficult to train and large part of the model that sits at the beginning, so closest to the original image data. And what the model does in the beginning tends to be the same across different tasks, different applications, right? So let's say you train the neural network to recognize celebrity faces, or you train it to recognize handwritten digits. Those beginning layers are doing kind of the same thing.
Same thing, yes.
So now, if you want to turn your neural network that was trained on celebrity faces to categorize the style of decor in a room, then you don't have to retrain the millions of parameters at the bottom. You just need the stuff at the top.
Okay, gotcha.
Right, so that's called transformer learning. And there's far fewer parameters at the top, so you don't need as much data. So you want something like that, powerful like that here. So this embedding thing, that's like the bottom layer, right? So in vision models, what do the bottom layers do? They look for edges, orientations. Our own visual cortex works the same way, by the way. You're integrating lines, finding shapes, building bigger patterns from smaller ones. So this maybe never has to change, whether you're translating, predicting the next word in a sentence, or we use multi-head attention even in vision models too. But, yeah, so you have this sort of modular framework. So the parts where you have the most parameters, hopefully you can reuse them across applications.
Yeah, any question? please. No, yeah, not easy. But really, no question or comment? So what do you think? You understand the element or still curious? We need to study further, right? So, but thank you, Mina. You begin the element, bring the keyword to our journal club. I think someone has to start that. So maybe, yeah, for those who haven't decided journal club topic for use, maybe you can do the follow-up some element thing, because now we learned the ABCD. So if we do the one more time, maybe we can understand better. Okay, so try it. Okay.
Has anybody used this in the biomedical space?
I
Well,
think
I don't even
there's
know what you've used this for.
there's
lot.
actually a lot.
What they listed.
There's even like single cell data analysis.
Partly because just think about the DNA is also
Sentence.
sequencing,
Exactly.
sequence,
Yes.
and protein is also sequence.
Yeah.
Messenger RNA is sequencing. So kind of now if you're searching, now you can find that kind of word a lot. Methylation GPT. They can predict which part will be methylated and then methylation in which region causing a certain disease, blah blah. Kind of anyway, everything is sequence in the biology. So they use this attention square thing in the same way to understand the language of biology. Yeah, that's a lot. Yeah, it's very natural, right?
Cool.
Yeah. So because this DNA sequence or messenger RNA sequence, we have to understand in terms of context. Right? So that's why LLM has been very successful. Yeah. So indeed, yeah, if someone can, actually recently I uploaded a couple LLM paper regarding that application in our team chatting. So if you, brave man or woman, why don't you try it like Mina? Okay, so let's thank to the brave Mina. So who is the next?